Okay, so we're live on YouTube.
Okay.
It is recording. So we're ready to start. Yes, so today we have Robert Oeckl. Thank you for accepting to give us this last talk of the pilot series of the virtual seminars. Who will be talking to us today about what is quantum theory. Robert, before I give you the, before you start your talk, I want to say just a couple of things about the next series, which is that, so we will be announcing, we will be doing it regularly from autumn, next autumn and winter. We already have a partial program on the website on QISS.fr, which is the speakers we have right now is Alejandro Perez, Nick Haggett and collaborators, Natalia Ares and collaborators, and Yenan Ismail. And there will be one or two more talks, so 5 or 6 for until December. So we hope to have all the talks announced in July or August. And the program will be available on the website. So I remind the format that it is, we suggest a 30-minute talk with short interventions only for clarifications during the presentation, and then there is plenty of time for discussion. So again, Robert Oeckl, what is quantum theory?
Okay, thank you. So yeah, thanks for letting me take the slot here for the talk. So the title is What is Quantum Theory? Let me share the slides with you. Okay, let's put this into presentation mode. Okay. Can you see the slide completely?
Yes.
Wait, sorry. Okay. And so, well, the title is What is Quantum Theory? Of course, in asking that question, I'm supposing that you already know about quantum theory, at least in the sense of having worked with quantum theory. And so obviously, I'm not trying to give you an introductory lecture to quantum theory or quantum mechanics here. What I really mean with the title is that I want to address more what is the essence of quantum theory, or also what should we think that quantum theory is. Okay, so let me proceed. So, well, when you think of quantum theory, maybe the first things that come to your mind are things like Hilbert spaces, operators, the Schrödinger equation, the Born rule, and collapse of the wave functions, and things like that. So what I want to do today is, in talking about the essence of quantum theory, convince you that this is not at all the essence of quantum theory, and that rather this is more like a particular manifestation of what quantum theory is or should be considered to be. So if we go back in history, in particular to the founding papers on quantum theory and the founding work by Heisenberg, Born, Jordan, Bohr, Dirac, Schrödinger, and others. So one of the very first founding papers on quantum theory by Heisenberg has the following abstract. So it was in German, so I'll just read you the abstract. In der Arbeit soll versucht werden, Grundlagen zu gewinnen für eine quantentheoretische Mechanik, die ausschließlich auf Beziehungen zwischen prinzipiell beobachtbaren Größen basiert ist. Okay, so as I suppose the majority of you don't speak German, I put a translation here. So in this work, it shall be attempted to obtain foundations for quantum theoretical mechanics which are based exclusively on relations between quantities that are observable in principle. So the key here that I want to emphasize is really quantities that are observable in principle. So for Heisenberg, and in fact, one could say the Copenhagen school of quantum theory, the emphasis was on the observables and the process of observation. Let me clarify a bit more what I want to, the direction in which I want to drive this here. Okay, can you just confirm that you can see this image completely? So there's a tree, there's an eye observing the tree, and there's a brain with an image of a tree in it. So what is this about? Well, I took this from a website that explains human vision, but I want to take this as a paradigm for really the act of observation of the natural world. So, so in this, so what we see in this image is basically where there's a tree there, and so the eye is observing the tree, and so the light rays from the tree fall into the eye, and on the retina they stimulate nerve sensors which transmit the signals of the light detection through nerves to the brain. And what happens in the brain is that from these signals, the tree, the image of the tree is reconstructed. So when we look outside and see a tree, then this perception is really a reconstruction of the signals that the light waves or photons have produced on the sensors in our eye. So the point I want to make about this is if we take this as representative of how we describe, perceive, and consequently describe nature, what we have is that we have the object, which is the tree, being detected in the eye, and then the signals of from this detection are reconstructed to represent the tree. Now, in the history of natural science, the object of study has basically always been the tree. It has been, well, okay, so we have to understand what is this tree, how it works, and this is the way we want to describe the natural world. The fact that there's this natural world out there was never in question, because it's so obvious when we see it with our eyes, that it's the most natural thing to say what I want to describe and understand in my pursuit of natural science is this tree. Now, when problems appeared in the physical description of our world, of trees and whatnot, light, that had this premise, with the advent of quantum theory, what we really appreciated is that the process of detection here is much more important than we would have liked to think. And so if we take this to the extreme, what we can do is we can shift our focus from the object to the perception of the object, or if you want, in more physical terms, the measurement. So what quantum theory tells us, in a sense, is that we should not focus as a primary object or as a primitive on the tree, but on the detection or perception of the tree, on the observation. What we can do now is we can elevate this to a principle in trying to describe nature. Okay, so instead of saying there's an object out there and I want to describe the object, I would say I'm perceiving something. There are signals, there are measurements, and I want to describe first the measurements, and whether the measurements allow me to reconstruct an image of a tree is then a secondary question. Okay, so taking this seriously, so I want to propose the following principles here. The primitive is no longer the object, and it has been in most of natural history, but is the observation itself, or equally importantly, interventions I can make. Now, to be as, let's say, as general and abstract as possible and as little prejudiced as possible, we can even put observations and then interventions together. And I want to do this and subsume this with a notion that I call a probe. Okay, so a probe is some kind of observation or intervention that I can make with respect to nature. So this will be my primitive. The second thing is that what I want to predict in a theory is the correlations between observations, between different observations, and also possibly between observations and interventions. The third thing I want to put forward here is that we should allow predictions to be probabilistic. So this being the more general case, rather than only considering situations where I can make deterministic or predictions that something will definitely happen or not happen. Now, sorry. Starting from that, so we have this element, this notion of probe, which is a fundamental notion and subsumes things like an experiment, a measurement, an observation, preparation, intervention. So we represent this with a box. So here on the left, I'll put kind of graphical representations of what I'm writing on the right. So we're now trying to set up a framework that starts from these principles with the aim to be a framework for describing nature. So probes, as I said already, may not only encode outcomes. So this is supposed to be a measurement instrument here with a pointer that points at some number, for example. This is supposed to be a switch. You can put it in different positions. And this is supposed to be a light that can take different colors. So it's also an outcome. Now, of course, probes are not isolated, and outcomes I could observe or will observe depend on other probes. And what we want to predict, as I mentioned already, are really correlations between these. Now, for a given set of probes, of course, the outcomes could or do depend in general on a large number of other probes, so other things that are going on around there. So one thing to simplify this is that I can put probes together and consider them as a single probe. And in particular, I can do this for all these probes that I could define as being external, treating them collectively. And then I'll also use the notion of boundary condition to describe this, although it's really a probe that is shorthand for a collection of probes that are outside. So in particular, to make this clear, a set of probes is itself also a probe. Okay, so now, I mean, this was all very qualitative, what I have been saying. If we want to go to quantitative context, in particular, we want to talk about probabilities for certain things to occur that we might want to predict. So we want to use these probes to do that. Now, it turns out, if you think about it, you realize that just setting up a set of probes with specified outcomes and inputs is not enough. You actually need two sets. So on the left here, you see basically the previous picture we had, which has various probes. It has a boundary condition, which is also a probe. So I use the symbol of a thermometer for the boundary condition because this would be kind of typical ingredient of a boundary condition, let's say the temperature in your lab. And here we have, so this switch in position A, this light is green, and this pointer points to maybe the number 2 here or something, the 2 volts or whatever that could mean. Now, to make that into a question that I could answer with yes or no, for example, is not sufficient to specify these objects. I also have to specify a reference with respect to with which I want this to compare. So, for example, if I take the reference on the right-hand side, what this means is on the right-hand side, I don't care about the color that this instrument will show, and I don't care about the pointer position that the instrument on the top could show. So this would be admitting all possible pointer positions and all possible showings of the light here. And so if we take these two pictures together, then these will allow us to form a question. And the question is basically, now given that the pointer position is, the switch is in position A, and given that we have this temperature, what is the likelihood that we see the reading 2 here and also the green color here? And the likelihood, so the point is now that each of these diagrams really will encode a real number, in fact, a positive number. And the quotient of the 2 is precisely the probability that we are asking for. Now, to emphasize again the importance that we have these two pictures, that we need these two pictures. For example, if on the right-hand side, we put this instrument here with a green color, and this instrument with a pointer still without any definite outcome, then the question we are asking is a different one, and the probability we're getting is also a different one. Then the probability is, given that the switch is in position A and that the light is green, what is the probability to read off 2 from this pointer device? Which is a different question than the one we asked before, and also has a different answer. However, the picture on the left is the same picture. Okay, so this picture alone is not sufficient to specify the question. We need both pictures, which is represented below in this quotient. So on the right-hand side, there's some kind of more formal expression, that some mathematical symbols that you could have used to encode this object. And there's a kind of composition going on between these probes, and it yields a real number. So this is basically what we want. So there's one more technical ingredient to do this, which I have not mentioned so far, which is that of an interface. So we can model the correlation between the different probes by connecting them explicitly with what I shall call interfaces, which model interaction, communication, or information exchange between probes, depicted as a link. And then what we have are networks represented as labeled graphs. Okay, here I didn't put the labels. So the significance of talking explicitly about these interfaces will become clear later. So in the picture above, in this one here, you can just think that everything is connected with everything else, and it doesn't really show up explicitly. It's all implicit in the formulas. What we arrive at with proceeding in this way is what I call the positive formalism. And the key mathematical ingredient turns out to be that of a partially ordered vector space. So these probes are positive elements in partially ordered vector spaces, and the interfaces carry partially ordered vector spaces. So why partially ordered vector spaces? So a partially ordered vector space is a vector space that also carries a partial order, obviously, which is compatible with the vector space structure. So where does this come from? It basically just comes from the real numbers, because real numbers model probabilities. And also theoretical physicists like to say that real numbers or sets of real numbers can be used to model any kind of measurement, right, outcome. Okay, so basically with real numbers, we can do everything. And this is where this partial ordered vector space structure comes from, because the real numbers form a vector space in particular, and they are ordered, but in particular partially ordered. And this is inherited by these vector spaces. Then there are some further structures in a product and an order unit that I don't want to mention. For this all to be consistent and coherent, there are conditions that these probes have to satisfy in these interfaces, and they can be formulated in terms of an axiomatic system. Now, what is a physical model that is modeled in this framework? Well, first of all, I have to specify what all these probes, what probes are there and what are the possible connections mathematically. And then I also have to say which of these probes and in which sense I can identify with experiences that we can have in terms of observations, interventions, and so on. So this
Robert, do you take a technical question just to not be lost?
Yes, sure. Please go ahead.
What partial order you have in mind here? Which order of a vector space are you referring to?
In fact, I'll give an example in, I think, the next slide. And so maybe just postpone the question to the next slide. And if it's unclear, then ask it again, please.
Sure.
Okay. So here's the next slide. And so here I'm giving an example of a partially ordered vector space, and it's probably the simplest and most important example. Namely, you take a set, and now you take the space or the vector space of real valued functions on the set. And this is a partially ordered vector space, because a function is larger or equal than another function if its value at each point is larger or equal the value of the other function at that point. Okay, so this is the partial order here. However, it's very important to mention that in the general context I was talking about, I have not made any assumption about the further structure of these partially ordered vector spaces. And I'll come back to that point soon again. Now, sorry?
May I interrupt you just with you mentioned an inner product earlier. Is this not assumed, or you said?
Okay, so the thing is that unfortunately I don't have time to show you in detail how you get these structures. So because I have it's a very short overview talk, so but if you want, in the question time, I could go into more detail.
Yes, perhaps we could go into these questions first during the discussion.
Yes. Okay, thanks. Okay, so back to this kind of most important example of partially ordered vector space. So a space of functions on a set with a partial order, and also, of course, the vector space structure of you can add functions and multiply them with scalars. And then if you want to be a bit more sophisticated, then this inner product in this case, so you'll also have a measure, and the inner product will be an L2 measure. Okay. Now, the important thing I want to say about this is that this is also what's known as a lattice. A lattice is a partially ordered set where for any two elements, you have a minimum and a maximum, which of course is the case if you have this space of functions. So if you have two functions, you can take the minimum function, which at each point takes the value of the minimum of the values of the two functions, right? The interesting bit here is that this also works the other way around. So if you have a partially ordered vector space with this property that it always has minima and maxima, then it has automatically the structure of the space of functions on a set. Okay. So now, even though I haven't talked about any particular physical theory, we are ready to return to the picture with a tree. So the question from this point of view now is, now that we're describing everything in terms of the detections and the observations and maybe interventions that we do, can we reconstruct the tree from this data? And basically there are two options now, namely the partially ordered vector spaces that we have are lattices, and then in fact there's a tree, or they're not lattices, which means there's no tree. Okay, so let me explain this a bit more in detail. So this is kind of a crucial point in this talk. So if the partially ordered vector spaces are lattices, so that means they are functions on sets, they admit an interpretation as statistical distributions. Okay, and in particular, we can reconstruct the set or space which there are distributions on, and this is then exactly the space or set of trees or states of trees. Okay, so the tree here is really this. So it doesn't really matter if we talk about trees or other objects, and it doesn't even matter if we talk about a particular classical theory of trees. It's a very general statement. So the other situation, so if we don't have a lattice, then there cannot be any tree, because if there was a tree, then all the probabilistic statements that we can make about it, about observations, interventions, and so on, with respect to the tree or trees, would reduce necessarily to the manipulation of statistical distributions of trees or states of trees, which means that these partially ordered vector spaces that we have would be precisely spaces of distributions and would thus be lattices. Okay. So basically, the point is that if there's something out there like a tree or whatever object or motion or whatever it is, then these partially ordered vector spaces have to be lattices and vice versa. Okay. Now the possibility, so the partially ordered vector spaces can have a range of structures. Okay, so they're not all alike, and they are not all of this lattice type. Now, one area where this is explored extensively is in the context of generalized probabilistic theory, theories which many of you will be familiar with in quantum foundations, which explores precisely these different possibilities in a more restricting setting of time evolution or dynamical systems point of view. Now, what we are interested in here now is the particular setting of quantum physics. And it turns out that this is the setting of anti-lattices. So in all the possible partially ordered vector spaces that there's a kind of opposite extreme to lattices, which were dubbed anti-lattices by Caddison in the 50s, which have the property that any two positive elements have a minimum or maximum only if they're proportional to each other, in which case one of the two will be the minimum and the other the maximum. So this essentially implies, if this is the case, it means that this partially ordered vector space is essentially the space of self-adjoint operators on a complex Hilbert space. Okay, so this is where the Hilbert spaces of quantum theory come from. And also, okay, some more details. So this inner product is then the trace of a product. And what does mean that one element is larger or equal than another one? So remember, these are self-adjoint operators. So one is larger than the other if the difference is a positive operator. A positive operator means that it's it applied to a vector and taking the inner product with the same vector always gives you a non-negative result. Now, this is, of course, exactly the realm of quantum physics. Now, about this positive formalism, so far, I have talked about this in a very abstract way. Talking about these interfaces that connect the probes and that mediate, if you want, communication or information interchange or interaction, what you want to call it. So to go to a more realistic setting, you can introduce a notion of space-time and of locality, which allows you to say, so you would say, okay, a probe now occupies a space-time location or a space-time region, and then you allow probes to be connected only if they're adjacent. Okay, so this is supposed to be represented in this picture. And this is what I call the space-time positive formalism or local positive formalism, which is, yeah, okay, I don't want to say more about this for the moment. Now, if you add furthermore that you're not interested in a general space-time setting, but you are having a fixed notion of time, so you order everything in time, then you can recover the usual, what's called the convex operational framework, which is very well known to people in quantum foundations and quantum information theory that work with generalized probabilistic theories, because this is where they live. And now, as I said already, we can have different types of partially ordered vector spaces. And so in the classical case, this thing here will just be classical statistical mechanics. In the quantum case, this will precisely recover the standard formulation of quantum theory. Okay, so I have prepared a few more slides to explain to you how you recover the standard formulation of quantum theory. Maybe I show just one or two. So this is a picture that might look familiar to people working in quantum foundations or quantum information and working with diagrammatic representations of quantum theory. So basically in this setting where you have an absolute notion of time, the time gives you a notion of order, again a partial order, which doesn't have to do anything with the other partial order I was talking about. And then you can put arrows on these links, and you can interpret these probes as linear maps, and you can compose them in different ways. I mean, horizontal, vertical, giving rise to the tensor product or composition of maps. And then you can talk about these partially ordered vector spaces at each instant of time as you can call them state spaces. Okay, so this is exactly how this relates to the standard notion of state space. And then you can think of these probes as giving rise to time evolution and to measurements, and yeah, in this setting. So, and then if you think about a measurement, you remember that you needed two different diagrams to describe a measurement. One where you specify what exactly are the outcomes, and one where you just specify that you're putting a measurement instrument there, basically. And the probability for an affirmative outcome is a quotient. Now, there's this additional ingredient that you can have, you can add in this time evolution context, and that's implicit in the standard formulation of quantum theory, which is a notion of causality. And this basically restricts what types of probes are allowed in a certain way, and allows you to normalize these objects in a certain way. And if you do that, what happens is that in this quotient expression, the denominator becomes equal to 1, and you don't see this denominator anymore. So by the way, the numerator here, this strange expression would in the quantum theory just be the trace. Okay, so this would be a trace, and the denominator would vanish. And in this way, you recover the usual expressions for probability in quantum theory that you usually think of as being linear, right, and not quotients. And this is only because you have this additional causality ingredient, which allows you to normalize things so that you can always eliminate these denominators. Now, reconstructing the standard formulation of quantum theory, some further steps are, it turns then out that the probes in this time evolution setting are precisely completely positive maps. The Born rule arises as a Bayesian updating of a state, okay? And that also gives rise to the collapse of the wave function. It's just an updating. By the way, in the classical theory, so if your vector spaces are lattices, this and have the interpretation of statistical distributions, this is just the usual updating of a statistical distribution when you gain knowledge about your system. The Schrödinger equation is just arises if you think, so if you have a certain time translation, for example, you have time translation invariance, and then these probes, which are completely positive maps that encode time evolution, they will form a quantum dynamical semigroup. And if time evolution preserves the inner product, which is what you conservation law you usually have, then it's generated by a Hamiltonian operator via a quantum Liouville equation. And the pure state counterpart of this is exactly the Schrödinger equation. Okay, so let me just leave two main references there on the screen. And so at this point, I'd like to open the discussion, and thank you for the attention. Thanks.
Okay, thank you very much, Robert. So today we'll not have a commentator. We'll go directly, we'll try directly the discussion session. So I think we can go to Onian and Carlo, perhaps, if, yeah, I think Onian still has a question. And feel free to interject if you want to raise hand or write questions in the chat. Yeah, I will try to catch Robert's attention. So, Onian, do you want to?
Thank you, Robert, for the nice talk. I actually have two questions, so I'll use this opportunity to ask them both. The first one is the technical one, which I asked about the inner product. It seems to me that, at least from my own understanding of quantum theory, I mean, this inner product, the only is not a very natural one, but I might be wrong about that. So I was wondering if you could just give a little unless you impose some kind of symmetry, like reflection symmetry. If you impose some kind of reflection symmetry with respect to these boundaries, I think I can understand how an inner product can arise, a specific one. It would not, however, I believe, exactly coincide with the Hilbert-Schmidt inner product which you wrote. So I was curious if you can give a little details about.
Yeah, okay. So thanks for the question. And in fact, the answer is something that you've already partially said yourself now. And it has to do with symmetry, in fact, but it has to do, so we're talking about this inner product here. So let me try to very briefly say how this arises. So if you take, unfortunately, I don't have pictures ready now to show this. So if you imagine a probe and you connect it on both sides with links, so you have a box and you have a line on each side. And now I didn't mention this, but there's a particular kind of probe, which I call a null probe, which basically doesn't do anything. It's just a means to do nothing and observe nothing, and nothing happens. And then what you want is that if you take this particular probe and you connect it on both sides, that this should be the same as just having a pure connection without anything inside, without any probe. And so the two links with this particular probe should be just the same thing as a simple link. Mm-hmm. And this is basically what defines this inner product, because associated with the links, we have these partially ordered vector spaces. So it means it gives you a map from 2 to 1 in some sense. Okay, yeah, unfortunately, it's a bit difficult to explain this without, I mean, I could look in some other talks if I can find this picture for you that explains this a bit better, but basically, this is the thing, and the symmetry that's at play here is has to do with the fact that in some sense it looks the same from both sides. So these links are not, so you don't have a distinction between the two different sides of the link. I mean, they're just
this is the reflection symmetry, I suppose.
Yes, yes, and you can think of that as a kind of reflection symmetry, which then means that this is will be symmetric. I mean, you can, okay, you can justify this better if you introduce, for example, a notion of orthonormal basis for these spaces, and then think more explicitly about how you compose them, and then you so on the mathematical side, the inner product just arises because yeah, it comes from this notion of composition and of this with a kind of self-duality that you have there, which you call reflection symmetry.
Okay.
I mean, if I wanted to explain this better, I would really have to go deeper into the details here, but I don't have slides ready for that now, fortunately.
Okay.
All of this work that we have on time reflection and this related formalism, which is essentially a version of what you described. I mean, this was an essential issue. I mean, we have on both sides of the boundary, we have kind of two dual spaces, but then one needs an extra map. Without that, there isn't a natural isomorphism between them. It's just two dual spaces, so you need some extra notion of how you take one probe and flip it around, I guess. But somehow that would,
yeah, okay, maybe I can say something more in this direction. So if I mean, many people work in a setting where you have, for example, time evolution, and you think of, for example, in one slide, I was alluding to that here, using a language that's often used in quantum information theory of preparations and effects. And usually you think of these as different, a priori different types of objects that don't, so basically what I'm assuming here is that there's a duality between them, and the duality is not something that I impose, but it comes from the fact that I start out in a setting where I don't have this time direction. So if you don't have the time direction, there's no sense in which you can privilege one ordering over the other if you make a composition, and it necessarily has to be the same. And then when you introduce time, this duality is conserved. Okay, so it's inherited from the fact that you come from a setting where you then don't have this time direction. So if that makes it clearer. So if you a priori say, okay, nature has this time direction and I work in this setting, then there's a priori no reason to say that these two should be the same. But if you say this time-directed setting is just a special case of something more general, then it's different. And then this more general setting tells you that there must be this duality, because in the general setting, it's just the same object. And now you're just orienting it with respect to this structure you've added, which is the time, in a different way.
Robert,
yes?
Can I make a naive question at this point? I'm not sure if it's going to make sense, but do you have a dual notion of the discard operation?
Yes, I do. In fact, the very same object can be also used dually. Of course, this is not very common in reasoning about quantum theory, and so in this time-oriented setting, what you would usually do is you would impose normalization conditions on states, right? You would say a state is a positive operator that has trace 1, okay? And then, of course, in the discard operation, what you have is something that looks like a state, but it's the identity operator. Now, if you're in an infinite dimensional setting, this has infinite trace. I mean, it's not trace class, right? Which would cause a technical problem. Or even in the finite dimensional setting of dimension n would have trace n. But again, this normalization of states and related to that, the different treatment of preparations or effects is from the general point of view, is just an artifact of imposing this particular time direction. And there's a way to deal with the infinities that you could possibly have when you make general compositions, which I don't want to get into yet. But maybe so this maybe answers the mathematical side of your question, but maybe your question also has a physical aspect to it, namely so physically, maybe I should emphasize this. So the discard, the physical meaning of the discard is that you say, okay, I have prepared something, I've made some experiment, and what I'm doing now is I'm throwing away the system. That means I'm not interested in anymore with what happens with the system. And the mathematical object that expresses this is precisely the discard. In other words, what the discard means is that it's a boundary condition that tells you that you don't know anything. So you're saying, I don't know anything about the future, and I don't want to put any knowledge about the future in here, so I use the discard, because that encodes precisely that I have no knowledge of at all. Now, in principle, you could also put this in the past, and you could say, I start with a discard, and I don't know anything about my system, okay? And in some settings, this you can make perfect sense of that. But often what happens is that, for example, so in particular, if you're in an infinite dimensional setting, what could then happen is that you don't get any definite outcome of your experiment, but that is because it's underdetermined, to put it like this. So for example, if you start with a discard, and then say, okay, but I make a measurement that ensures that my system is within this set of possible states, and then you make another measurement, then you get something finite. And then the discard in the past just has the effect of randomizing over these initial possibilities. And so if there are just n different possibilities orthogonal to each other, then each will have a probability of 1 over n. But of course, in general, it's something that we are not accustomed to think of. We are not accustomed to think of that we have no knowledge of the past and that we still want to make some statements about what's happening or what we measure or something like that.
This is actually related to my second question, if I may use it. Shall I go on? Shall I ask
Yes, let me just say that we still have 35 people in the Zoom, and there were 15 people at YouTube. If you have questions in YouTube, you can write it in the chat. And there is Ding Jia that is waiting in line, and Carlo Rovelli. So yeah, Onion, if you can.
Okay, so it has to do with this causality and the reversive, the inverse of the discarding effect. So, so there is something, I mean, we can define this inverse, of course, and of the discarding effect, but there seems to be something natural about the fact that there is this discarding effect, which is unique forward in time, whereas backward in time, we need to just define what it has to be. It does not arise naturally. And I think this has to do with the fact that in our usual situation where we have a well-defined time going on, I mean, this really corresponds to what we may know. This is our best knowledge about the future unless we do any post-selection. Whereas back in time, we do not have that. And it, so what I was wondering is about your view on causality. Is it something that we just impose as a property, way of describing physics, let's say in causal terms, or do you see it as pertaining to some feature of the world, which, for instance, does not hold back in time, but it does hold forward, as I was trying to say?
Yeah, of course. Yeah, this is an extremely good question, which also I don't have an answer to, but I can try to make it more precise in the present setting. So I don't know if you can see now this slide which says causality. Wait, let me.
No, we're seeing elementary diagrams.
There's some. Okay, let me see if this sharing thing. Wait. Why does it say pause?
Robert, can you hear us? We might have lost Robert. Seems to be some issue with the connection. Gonna stop his screen sharing. Yeah. So let's give him a minute, see if he's going to reappear. Robert, can you hear us? You have to unmute.
Okay, sorry. Yeah, it was muted. Yeah, I managed to crash Zoom. Well, so okay. Can you see now a slide I'm sharing?
Yes.
Yes.
Which says causality or not?
Yes.
Yes.
Okay. Yeah. Okay. So this is just a kind of technical slide that says what is technically this causality condition. So basically, it means that if you have an operation and you compose it with this discard operation, then this will be the same as the discard operation if the operation you have is non-selective. So non-selective here means that you're not asking for a particular outcome. So you're just measuring something maybe, or setting a knob setting or whatever, but you're not taking into account an outcome this might have. And then you impose this this condition, so the meaning of this, or the consequence of this, is that basically if you do some experiment and later on somebody else comes into your lab and does a different experiment, this does not influence the results that you obtain. Okay, so if the other person that conducts an experiment after you tells you about the results that she obtained in her experiment, then this could change the outcome probability for your predictions for your own experiment. But if the person doesn't tell you anything about her experiment, it doesn't matter what experiment she performs, it will not change the predictions for your own experiment's outcomes. And this is precisely what this this condition ensures, this causality condition. And this causality condition is time asymmetric, right? Okay, so sorry, Ongyan, maybe we can come back to your question. So could you say it again?
Yes, I was. I mean, it's my question was whether you see this as a natural property somehow, a physical property of some sort, and whether you see it as, yeah, how you understand it. Is it just a matter of us defining it and then going on, for instance, describing the world in convenient causal terms, or does it reflect some property that is out there? Yeah, how you see that property, perhaps.
Yeah,
Robert, before you answer the question, I suggest we turn off the sharing of your screen so we can go to conversational mode. And then after that, we can go to Ding Jia.
Okay. Okay, so this time it didn't crash. Good. Okay. Yeah, so it's a very good and a very deep question, and I've obviously thought about it, but also I don't have an answer really. It does seem to reflect an important experience that we have, and important data about our experience with the natural world, right? I mean, empirically speaking, this is, we never observe this acausal behavior that otherwise could be occurring if we didn't impose this condition. Now, this condition, of course, so the question is now, how does it arise? Is it something that we have to put in as an additional ingredient, or is it something that should be naturally coming out of the physical theory that we're considering? So, well, let me say something else first. So if we go away from this particular time evolution context, it's very clear that this condition in this form cannot be upheld. Okay, and this is extremely important to appreciate. So if we go to a context where we have no predefined notion of time, let's say we want to do quantum gravity, then it's absolutely clear that this condition in this form doesn't make sense, okay? Because we don't have a notion of time, we don't have the partial order of time, and so this also a message that on previous occasions I've tried to emphasize, and this is one of the reasons why when you talk about these probabilities and extract probabilities, in the absence of this causality constraint condition, you cannot neglect denominators in probabilities, absolutely not. And probabilities in general have to be quotients in the way I described it. Now, if you look at quantum field theory, for example, there's nothing in quantum field theory at the mathematical level that suggests that there should be such a condition. On the other hand, if you take quantum field theory and you restrict yourself to observables that arise from operators at fixed times, then or measurements that correspond to operators that you have at fixed times, these measurements always satisfy this condition, and also the reverse condition, by the way. So it's in general unclear how this condition can arise. You can ask, for example, the question, is there a way to impose such a causality condition in a context, if you want to impose it, where you don't have a definite notion of time? And so I have tried to address this question 2 years ago at PI. There was a conference on foundation of quantum theory. In my talk, I tried to give a possible answer to that in the context of fermionic theories, where you can indeed impose a condition of this type without having a fixed notion of time. But so if you're interested in that, I mean, you could listen to my talk, which is in the PI archive on that. But in general, I don't have an answer to the question. So let me put it like this. Thanks.
Thank you very much.
Ding Jia.
Hi, Robert.
Hi.
Hi. It's nice to talk to you again. Nice to begin. I like to talk a lot. I like to work a lot.
Thanks.
Spending more and more time studying your work, and I realize more and more depth and significance of your work, to the extent that I'm almost converted to a positive formalism person, or general boundary formalism person. But some questions remain. This one is about quantum gravity. So when you introduce the positive formalism in your talk, you mentioned two ways. One is the abstract way, which uses graphs, and the other is the space-time way, which assumes a manifold. There doesn't have to be a metric on it, but we need a manifold structure to define boundaries on the manifold. And in your previous writings, I think you mentioned that maybe the space-time way is preferable because when we consider gauge theories and manifolds with corners, there are some subtleties. It seems it's better dealt with in space-time formalism. And I think this is relevant for quantum gravity because a lot of the approach is background independent. Quantum gravitational approaches like spin foams, causal dynamical triangulation, causal sets, etc. They are based on graphs. And in some of these approaches, a manifold structure is not assumed. And if it is the case that the space-time manifold picture is preferred, then it seems there's some extra task for the quantum gravity people to address. I wonder, what's your thought on this choice now? Is there any message you want to deliver to the quantum gravity people?
Yeah. So about the particular question of structure between, on the one hand, manifolds, and on the other hand, just having graphs. So first of all, of course, having manifolds also allows you to draw the corresponding graphs, right? This, of course. So the other thing is that there is, in fact, it's not just two extremes, having either a manifolds or only graphs, but there's a kind of whole spectrum that you can imagine in between. So the manifolds, I assume, at least at the axiomatic level, usually are just topological manifolds, right? But you could weaken this further and talk about certain types of complexes. And So there's almost a continuum, or I mean, there are many different possible generalizations where these graphs are kind of one extreme and the manifolds are another. And you could look for intermediate steps where you have a little bit more structure than the graphs. So you have some kind of dual n-2 cells or something, but not more. Or as for the significance of not just having graphs is indeed you mentioned it already yourself. When you are considering gauge theories, then the additional structure of the manifolds, at least some of the additional structure, not necessarily all of it, becomes relevant. You already mentioned corners, because you, in that case, you have to be able to associate data with these corners. And this indeed is lost if you just look at graphs. So so basically, yeah, I can just confirm what you were saying in that respect.
So it seems there are some recent works on edge modes in quantum gravity.
Right. So I have to say I haven't looked in detail at that, but I think that's probably quite important.
And do you see because it doesn't seem there's a no-go theorem that says, if you just have abstract graphs, you cannot incorporate gauge theories. Do you see there's some potential that even if I deal with graphs, I can somehow incorporate the degrees of freedom that would otherwise be associated to the corners, and then just have a consistent and meaningful gauge theory even with graphs?
Well, I think that would be difficult. I think you do need, maybe not necessarily the manifolds, but you need additional structure to encode these additional degrees of freedom that rise. So I think, I think you need something more than graphs, definitely, when dealing with gauge theories.
Yeah, I'd like to discuss this with you more, maybe through email.
Sure, we can discuss this at some point. Thanks.
Okay, so Carlo, I think had a question. Let me say at this point, because there is a question in the chat, which perhaps Robert would like to say a word. There was a question on what you meant by a fixed notion of time.
Okay, yeah, with a fixed notion of time, I basically mean that you're having a coordinate with a real value, which you call time, and that you organize that the physics is described by what happens in time. So at each time you have, say, a state space, and then the evolution of your system is described by describing the evolution of these states in time. Yeah, so that's basically what I mean with a fixed notion of time.
Okay, thank you. Carlo, did you have a question?
Yeah, thanks. I have two comments, Robert. In fact, the first one, it's good that it comes after this question. First one is that I think that the work you have done, the work that Robert is doing on this formalism for quantum mechanics is it's extraordinarily good, and it's very important. And the way I view it is just stripping the structure of quantum mechanics from those parts which are more contingent, like, for instance, the existence of a preferred time variable, and taking up the part of quantum mechanics, quantum theory. There was a question in the chat, somebody asking what is the difference between quantum theory and quantum mechanics. For most of us, these are synonymous, but in the community, there are some people who use quantum theory for the general quantum theory and quantum mechanics just for particles with a Schrödinger equation or something like that. So it seems what you're doing, Robert, is taking quantum theory and making it general enough to deal with situations where there is no time, there is no manifold potentially, and so on and so forth. And this is working super well, in my opinion. And in fact, as you know, we're using your way of thinking repeatedly when we compute, black hole to white hole probabilities, probability in which sense? And I think your clarification that probabilities are ratios in the way you said, it's right on the spot. It's very clear. And the point here is not to explore potential alternative quantum mechanics. That's not the spirit. The point is take it out of quantum mechanics what should remain when you do quantum gravity, because that's where we want to go. So that's the first comment. The second comment, I want to make it before, but it's strongly related to the question that Ongyan were posing, and that you said, well, I'm not sure about the answer. From my perspective, and I presented just a discussion, not as a criticism, there is something missing in the story you present, or in the perspective, not in the actual mathematic. But I would say in the first two slides of your talk, which is the following. And this missing point is exactly what addresses the questions about causality, about direction of time that Onion was posing. So I want to say something about that. And this is also related to a paper that Andrea Di Biagio and Marius and Pietro should finish soon and talks about that. Somebody's laughing in the audience, I see. So the point is the following. When you say we have probes, how you call it, and you gave a nice intuitive introduction to probe with the tree, the retina, and the brain. Okay. That's very clear, except for one thing. What the physics of the brain, what the physics of the other side of the probe. That's what you sort of, you introduce this notion of probe, very clear, and then you forget about it forever, which is fine for what you're doing, but leaves some open questions, in my opinion, which is the fact that either you read this in a sort of German idealistic philosophy in which there is a spirit outside nature that sees and observes and probe, which somebody might want to go in that way, or you interpret this in a naturalistic setting in which the agent which is probing, the observer of quantum theory, it's a physical system itself. And in fact, in a laboratory, it could be me, but in a galaxy where quantum theory is going on, is whatever is interaction thing with whatever else. So, of course, I read quantum quantum theory in terms of relational interpretation, which is a way to address that, which is, of course, is compatible with everything you said, except to the point that the probes are not with respect to Robert Oeckls' brain, or to the brain of humanity, or to the brain of God, but with respect to another system which they're interacting with. Now, once you do that, you realize that the observer has a physics. And in particular, in a laboratory, the physics of the observer is the actual macroscopic physics of the guy doing the experiments, which is dramatically time-oriented because we live in an entropy gradient, which is dramatic, and because we are dramatic time-oriented. So the observer brings its own time orientation to the reading of the probabilities that you are defining. You define these probabilities nicely and cleanly, and they don't need any direction of time. They need a direction of causality in the sense that quantum probability may be of the form if this, then that. So there is a precedent if and a consequence then that, but there's nothing that says that if should be in the past and that should be in the future. There's totally separate issues, the direction of implication from the formalism and the direction of time. Except that we are very much time-oriented. We remember the past. We try to guess the future. So for us, the if-then is always oriented toward the future. But that's not in the quantum system. That's in our eyes. Our eyes are not the eyes of God, who is time-oriented. We are not God, or Robert Oeckl, I don't know. But our eyes are the eyes of a macroscopic system which lives in a time-oriented macroscopic world, because entropy was low in the past, we don't know why. And therefore, colors of an orientation, the time symmetric, the time reversal symmetric probabilities that you're defining. The work with Andrea, Marius, and Pietro, we're trying to complete, it's to a large extent to just fill the dots in trying to understand how the specific causality postulate you're referring to has a time symmetric version, which is the right way to think about it, and what it means time direction independently, so to say. So this is the connection to Ongen's question, and the general point is that I fully buy your formalism, because I think we have to if we want to do quantum gravity. Pietro defended his thesis a week ago, and at the question, how is exactly probability defined here, he was sort of gasping, and the right answer was ask Robert. Robert knows the answer. But I would frame everything you have done in a context where we should not forget that the probe, it's an interaction between whatever you are describing and a physical system, on the other hand, which, of course, if we want, we can also describe with quantum mechanics.
Okay, so yeah, thanks for your comments and remarks. And in fact, so I think the characterization you gave first of what I'm trying to do was exactly spot on. So in a sense, it's precisely trying to remove the contingent parts of quantum theory that we have used in practice in most applications for good reasons, but which are hindering a possible formulation of quantum gravity in quantum theoretic terms. Now for your other point, yeah, so that was it's a very important observation, in fact. So yeah, so if we go back, I not put up the slide now because I don't want to crash Zoom again. So if we remember the slide with the tree and the eye and the brain, right? And you say completely justifiably that if we take this seriously, we can also ask, so the eye itself or the brain itself, they should also, we should also be able to put them in the position of the tree, right? And then they are suddenly play a very different role in the description. They are no longer themselves the probes or the primitive in the primitive category of how we describe experience, but they're just subjects of this description. I didn't say anything about this, and so let me say a few things about this, because this is really important. So thanks for insisting on this, because it is very important. So first of all, I'm not pretending that this way of approaching things is the best or the unique superior way, because somebody that wants to defend the position that the tree is the primitive object here could precisely say, well, your retina is also like a tree. So so what comes first, right? The detection of the tree, or the tree itself, or what, right? So the main reason why I'm defending the way I'm doing it is because it has been successful, and because quantum theory is precisely made in this way and has been extremely successful in describing nature at a microscopic level. So if you want, I can give this pragmatic justification for this taking this point of view and this perspective. Now, a second point is which has to do with more explicitly talking about the observer, more explicitly talking about whose retina is that or whose brain is that. So the way I see it, in a sense, in this approach, this is where the measurement problem lies. Okay, so for me, from this kind of perspective, the measurement problem arises because this retina here, or the detector, or your device, or whatever, can have two different roles in this whole context. One being in this position of being modeled by a probe, which is a primitive of this approach. It's just saying, well, this is a measurement device, and this is how we describe that. And the other way, of course, being in the position of the tree, right? So we have to find a way to bring these two in agreement, in the sense that we have to find a way to say that this or that type of tree, or this of type that, no, let me say the other way around better. So we have this detector there, which we can describe as a detector, but at the same time, so we have to have something like a map that maps us this to how this would look like if we would look at it from a different detector, right? So this kind of identification that comes with the change of role in the formalism, right? Of course, already at the beginning of quantum theory, this was an important question, and von Neumann, in his writings in the 30s, in particular of quantum theory, was already talking about this. I mean, what happens if you have a device and it has a pointer, and then you make a measurement, and then you want to describe the pointer device itself quantum mechanically, and have a different device that reads out the first device, and so on. And so he has managed to, in the context of the usual standard time oriented quantum mechanics, to kind of partially answer this question. But of course, it is very far from a general answer, where you could more generally say, now we have a probe or something that we identify with an observation, a detection or something, and how do we map this exactly to something that's observed? And so from my perspective, this open question is basically also what I would consider the measurement problem in this context. Now, you were also talking about a notion of time direction in that context. So I'm less sure about that, but I guess, so I'm looking forward to the work you're going to publish. I mean, I know you've thought about this question from a different point of view, and thinking more concretely in terms of, for example, the entropy. So of course, what I was presenting now is only at a very basic level, and not taking into account any specific physics. So the formalism, as I've presented it itself, doesn't say anything, for example, about how entropy evolves in time or things like that. So this would be basically additional ingredients, but it's very possible, and I think what you are saying goes into arguing that once we add those ingredients, then we can perhaps understand this notion of causality that we experience. Okay, so thanks very much for your intervention.
Marco is waiting for some comments.
Yeah, okay. So first of all, I would like to second all the praises of your work and the comments that Carlo and others have done. I mean, this is certainly very important, formalism, and as far as I understand, it is what people actually use in loop quantum gravity in an implicit way. Basically, it is the way of thinking that is behind the whole idea of the spin foam program and other programs. So it is a very good thing to explicitly spell out all the assumptions and all the structure that goes into it, so that we know what we are doing. Now, my comments, I had a bunch of technical comments along the way during the discussion, but I have forgot them now. What I want to comment on basically are two main things. One is related to the notion of causality that we have been discussing, and the other is related to this question of the measurement problem. Now, regarding causality, I wanted just to make a very short comment that causality is as a term, is sort of overloaded. Lots of things, people, lots of different things when they say causality, and in the context of your formalism, I would I think it would be best to, well, in a sense, avoid using the term causality altogether. I mean, that is my suggestion in a sense, because the way I, for example, understand causality is as a contingent notion on on determinism. So when you have determinism in your theory, you can say that certain events always happen in pairs, right? So you have a cause and an effect, and this can only happen if you can predict the future or the past from the present, and these kind of things. When you're working with the probabilistic theory, which is essentially what we are doing in this context, you can never say that there is a causal relation. There is only correlations, in the sense that correlation and causation are not the same thing, and so on. So that's just a short suggestion that maybe using the word causal and causality can be a misnomer. You maybe want to rethink the terminology. But regarding this measurement problem thing that is also under discussion here, I just wanted to say that it may be a good idea to think about this problem in the sense that whatever we do in order to interpret the results of measurements and these kind of things, we usually always need to split the whole universe into two pieces and then apply the theory, the formalism, only to one piece and declare the other piece to be called the observer. So how we split the universe into two pieces might be arbitrary, right? So you can choose this observer or that observer. I mean, this subsystem to be an observer or that subsystem to be an observer. But the problem itself is defined by the fact that it is necessary to make that split one way or another. We do not have a way to think about the theory without cutting the universe into two pieces and applying the theory only to one piece and not to the whole thing. Right? So that requirement that we have this intrinsically dualistic way of thinking about the universe, and the fact that we cannot apply the theory to everything, is, I think, the main property of the measurement problem. And maybe that, I mean, this is just a suggestion to everyone. Maybe it is a good way to think about that in those terms. And that very nicely correlates with your formalism, because basically in your formalism you have these little boxes, right, which represent outcomes of measurements, and the whole space-time or the whole graph or the whole manifold, regardless of the details, represents your quantum system, except the inside of those boxes. The insides of those boxes basically represent, at least some of them, represent the actual outcomes of your measurements, or the actual readouts of the apparatus, or these kind of things. And for the inside of those boxes, quantum mechanics does not apply, right? So that's the idea. Those are the observers. Those pieces of space-time are the pieces which we have cut out from the universe and declared to be an observer, right? So in that sense, it is natural to think about the measurement problem in the way I described in the context of your formalism. So maybe you want to comment on that, or I don't know if you have already thought about this.
Yeah, thanks. So first, so you were saying that there are different notions of causality, and indeed, of course, you're completely right. And the notion of causality that I was talking about is a very specific one, of course, only. But it is the one that plays a very important role in the standard formulation of quantum theory, because this underlies basically our ability to go from, I mean, in practical terms, to go from these quotient expressions for probabilities to apparently linear expressions. So in that sense, it is very very inherent in the standard formulation of quantum theory, and also in other attempts to say generalize or modify quantum theory. This is why I wanted to put a special emphasis on this here. But of course, you're right, it's only one particular notion of causality, and also as you pointed out, in the general setting, especially if we are in the space-time setting where we have no notion of time a priori, then we cannot talk about this condition, this causality condition in this way. It doesn't make sense, right? Now, about the measurement problem, yeah, I think what you're saying, basically, I would express it a bit differently, but basically the cut you're talking about would correspond in the way I presented it, basically in what also I talked already about is this distinction between the tree and the eye, or the eye and the brain. So it's not something that necessarily has a location in space-time. It could have, but doesn't necessarily have one. But this is this is also how I view the measurement problem, as not only talking about this distinction, but talking about how we can identify something that on the one hand acts as a detector with something that on the other hand is observed by another detector. Okay, so thanks for your comments.
Okay, thank you. There was a question in the chat by Ismail, although this may need a bit of context. The question is entanglement scale dependent? I'm not sure how, I don't know if Robert sees the relation. Ismail could unmute and ask the question or explain.
Hello, can you hear me?
Yes.
Yes, I was asking the question because you were discussing measurement, but
Yeah.
I was discussing the issue of quantum mechanics versus quantum theory. And I'm assuming that most of the discussion is on the small scale, but you're using a tree in the example, which is macro scale. And I was referring to, is that just an example, or are you actually, because it's a macro scale example.
Right.
So I'm trying to get a consistency between, okay, if we're going to use a macro scale example, okay, are we saying that entanglement or phenomena that is related to quantum mechanics or quantum theory can be extended to larger scales, because I do know that an experiment was done at the University of Chicago where they actually were able to show entanglement amongst particles, you wouldn't say particles, but about 20 microns. So they were showing that entanglement wasn't a phenomena that was, you could say, isolated to particles, small systems. So in your talk, do you believe that this phenomena also extends into larger bodies, which would open up a discussion for quantum gravity as such, because you would have a phenomena that's not actually bounded by scale?
Okay, thanks for the question. In fact, so when I was preparing the talk, I was actually thinking of inserting another slide right after the slide where I was with the tree and the eye and the brain, where I would have shown something similar. Now, let's say at the LHC, on the left, you would have particle beams and then a detector and then a computer that reconstructs the events. And so what I would have said is that if you look at the picture of the tree first, I mean, this is how natural science has been done for centuries before quantum theory, and there was not really a compelling reason for much of that time to question the role of the tree as the primitive object in our theory, that namely that the object is the primitive. And only when we were looking at much smaller scales, then we started to notice that this reconstruction that we would do of this tree would no longer work, right? I mean, when we talk about elementary particles and momenta, positions, angular momenta, energies, and all kinds of properties of microscopic systems, then it's precisely in that context that we really realize that the reconstruction of this classical object is no longer working, and we can no longer reconstruct consistent classical objects. And of course, it's true that if you go to large scales like the tree, then the classical prescription and the idea that it works well to take the objects or the tree as primitives is well justified. So of course, we know that quantum theory is relevant at all scales, but it is the world we experience is indeed very well approximated by classical theories at scales that when we go away from the microscopic scale. So yeah, so in a sense, I put the picture of the tree there, not because I would say that if you have a large scale object, then you would necessarily have a problem with this reconstruction, but that it represents all kinds of objects, and the problems that will force you to switch from classical theory to quantum theory, you will notice them only at small scales indeed. So thanks.
Good. Thank you.
Marius, you're muted.
Marius, I have a question.
I'm sorry. I was muted. So I was asking if there are any further questions.
Yes, I do.
Yeah, please go.
Yeah. Hi, Robert, again.
Hi.
I have a list of questions on my notebook. Right. So maybe on the first or second slide, you mentioned some things that you think are not fundamental to quantum theory, which includes Hilbert space. complex Hilbert space, I suppose.
So that was basically the first or second slide where it was just an enumeration of the structures that we are usually using when we do calculations in quantum theory, right?
Mm-hmm. Mm-hmm.
But I mean, part of my talk is, I mean, the intention of this talk is precisely to say that this is not what we should fundamentally associate with quantum theory in general, right? These structures, that these are only structures that arise in a very particular setting, namely when you have an absolute notion of time, and then it makes sense to formulate a theory in those terms.
So would you say the ordered vector space is a more fundamental mathematical structure than the complex Hilbert space?
Yes, definitely, because so I mean the formalism in general, and in a large part the way how I have presented it didn't in fact talk about classical or quantum theory in particular, right? I was first just talking about observations, how to organize observations and interventions using probes, and how to make a formalism with these ingredients in order to possibly describe physical theories, or which is a formalism where you could put in a physical model. And this is before you talk about classical or quantum physics in particular. And indeed in classical physics, which is perfectly compatible with this, and you will not have complex Hilbert spaces, right? You will have sets, and will have functions on sets. In fact, the sets have more structure. I mean, they're usually called phase space, right? So, so in that sense, and there you also have these partially ordered vector spaces, which are just the vector spaces of statistical distributions, right? So, so you have partially ordered vector spaces in more situations.
You manage it again.
Robert, can you hear us? Okay, we seem to have lost the speaker. Well, let's wait. If he shows up, at least we could thank him before closing the discussion.
We should thank him, at least clap to him. I mean, let's wait a moment, he comes back.
Yes, yes, yes.
So when are we starting again? What is the plan?
1st of September, and then it's every 3 weeks. The program is on the website.
Okay. Are you resending a?
Yes, we will send an email with all the talks. So Robert is back. And Robert, you have to unmute yourself. Yes.
Sorry about I had another problem with the software here. Okay.
Yeah. I don't know if you had if you wanted to continue the comment you were making before, and we could also close the discussion afterwards.
Yeah, basically, I was basically finished. I hope it came over more or less complete, what I was saying.
Okay, so then in that case, we can thank the speaker. Thank you very much, Robert.
Thanks.
And yeah, I wish everybody a very good summer and good vacations. And let's start again in September. So we will be starting 1st of September again with Carlo, probably, as we just discussed. And yes, the program is available on the website, and we will also be sending an email.
Stay safe.
Yeah, take care, everyone.
Bye.
Bye. Adios. Bye-bye.
Thanks, everybody.
Bye-bye.
Bye.
Thank you.
Hi, Robert. Are you there?
Ding, I think he logged out.
Yeah. Okay. I'll get in touch with him.
Sure.
See you guys. Bye.
Bye-bye.
May I ask something, Carlo, at this point, perhaps? Something he said? Is the discussion still open or we're finishing?
Give me a moment. I'm stopping the recording and the YouTube live.